After Hours is brought to you by Bridgestone Tires, solutions for your journey.
Gary, you ready to do another show?
Absolutely.
I am too.
It's going to be a good one.
It's going to be a good one because we're going to be talking about hydrogen and fuel cells.
The
powertrain of
the
tomorrow.
future.
The future of tomorrow.
The future is now.
Well, let's find out.
We know it's now.
Well, we've got Charlie Freese, who runs all fuel cell development at General Motors globally. We've also got Lindsay Brooke, our fellow colleague here. And Charlie, let's get to the bottom of this. I mean, we've all been writing about fuel cells. We, the journalists, for decades now, decades. And, we know so much about them, and it's always been, boy, in another 10 years, and this is probably the 30th of another 10 years that it just hasn't happened yet. Are we ever going to see fuel cells in vehicles?
Well, it's happening, John. Actually, yesterday, we just pulled the wrappers off of our plant that's over here in Brownstown. It's not too far from here. And that's the joint venture 50-50 with Honda, where we're producing fuel cell systems now. And those will go into Honda applications. They'll go into different places that we're installing fuel cells. And we've announced a few things in the last 6 months about different places that we're targeting to put the fuel cells. And one of the great examples is in autocar applications. So if you're not familiar with autocar, they make big Class 8 trucks, but these are not just semi trucks, which they do make, but it's also going into applications like cement mixers and dump trucks and refuse haulers and things that can really take advantage of what a hydrogen fuel cell can offer. And batteries would be much more challenged to do. So it's happening now.
Yeah, so I was actually there yesterday, and I mean, they literally have a factory, and they literally have people that are there. It's just like any factory you can imagine. The thing I've started wondering about, Charlie, is that what are the sort of skills that you needed to bring there to be able to do this technology that, we've been waiting, people have been doing this like making jewelry, right? I mean, like one by one, but now you guys have a production process.
Yeah, so there was a lot that went into bringing fuel cells to where they could really be production viable. And I don't mean as a curiosity. I mean, everybody knows that it's a really interesting way to make electricity with two invisible gases, oxygen and hydrogen. Everybody knows that. That's been done in the lab for a long time. But the trick is to make it something that you can scale for production. And we had to do a lot of work to develop the new designs as well as the manufacturing processes, borrowing from other industries as well. So we have the things that we know how to do as an automaker that's made high volume for a long time. We've had our partner Honda, all the things they've learned, all of that came in, but we also had to bring in some things that came from other industries. And one great example is the filmmaking business like Kodak. And so if you think about how you make film, which is layers that are deposited on top of each other, and in the case of also putting it on big roll-to-roll coaters, so that's like from the paper making business. So we brought those technologies together, and that allowed us to go in and start to build the capability to do very high volume production of the soft goods that go inside the fuel cell stack and do it at high quality. So even though this thing might be coming off at 7 meters of material per minute, we can scan it and find micron level defects and call those out if there's any manufacturing defect and avoid those defects propagating into the actual parts. All that had to be developed. So those are the types of things that we brought in. And I think you've been through our lab in Pontiac before. That lab is basically where we used it as a proving grounds for all the manufacturing techniques. So everything from the roll-to-roll coaters to the way that we do the quality detection on the membranes, the way we mix the inks that are printed onto these things, all of that, we did it in the lab in Pontiac. So right there where the engineers are doing the design and development, they're developing the processes right there alongside it. And that was a big enabler to making all this happen. And then the other thing is automation. So we've gone in. You probably saw the place where all the stacking of the fuel cell stack is done. So you take these big roll coats, coated material, which is the membrane with the electrode on the two sides of it, and then we take that out and we cut it and we shape it to the right size. We put on a gasket layer basically, and then it moves into this stacker, which is all robots swinging around. You can't even get very close to it because there's fencing to protect you from all the different robots, and all these robots are literally just going in here, 10-second cycle time reprocessing these parts into a stack, and it's quite amazing. And the engineers that have done all this hard work for all these years have really perfected the elements that go into making this design possible. And it's also scalable, so we can do something here that we're in a beginning of the industry cycle of this. It's not like we're building millions of them every year. So we have to allow ourselves the flexibility to scale up as demand develops, still using the same technologies that in themselves are designed to be scalable. And that's part of what we've done.
Charlie, in this long, I mean, I've been covering this since I think the 80s. And GM has always been in the forefront in terms of IP and just, subsystem and component development of the fuel cell. You got to a point where you had a thing called Project Driveway, which was actually putting fuel cells in, I think, Equinoxes at the time, if I'm correct on that. Racked up a lot of miles, a lot of user miles, real people driving these things. And then it seemed like there was kind of a period where we didn't hear much from General Motors, and we heard things from other automakers and so forth. And I even covered a fuel cell powered submarine for the German Navy that Ballard was developing. So these things were happening in different places. And you mentioned all these other industries kind of gaining knowledge from these other industries in terms of manufacturing and so forth. Was there a point that really kicked this off? Was it the partnership with Honda, or it seems like your program has accelerated in the last 4 or 5 years faster than it had in the past?
Well, that's a good point, Lindsay. I think if we go back to Project Driveway, that was a stack. It was actually 2 stacks. Every one of those fuel cell systems had 2 stacks. 200.
By the way, I drove that. I drove an Equinox, spent all day driving around LA in it.
Yeah, and it was a 220 cells per stack, so 440 cells inside one of those systems. And they were done on basically a carbon composite plate. And the membranes were in there heavily loaded with platinum. So we had over 80 grams of platinum in that fuel cell system.
Was this like Gen 1? Would you call this Gen 1?
We call that Gen 0.
Gen 0.
Yeah,
okay.
so that was basically proving that the technology had what it would take in the future once the problems are solved to kind of get you to where it needed to be, but also showing that it could meet the customer expectations. And that's really what Project Driveway did. It showed a 300-mile range vehicle that could go out there and refuel quickly in minutes. It could be in your garage. It could deal with all the safety and make it so it's not a special vehicle that you need. I mean, the very first time vehicles were fueled, they were fueled with people in hazmat suits and grounding cables and all these other things. I mean, we moved it to
a consumer level.
It's something that you could just do. I mean, I had it in my garage. My kids rode in it. It was no big deal, right? It was just standard how you use your everyday driver. So that was where we were at that point. We had to get much lower cost. The platinum levels in that 80 grams, that wasn't commercial.
The precious metals were unrealistic in terms of cost.
Exactly. So at the time, right around where I took over the program, Byron McCormick had done a lot of work along with Larry Burns. They were trying to get the technologies, understand what the future had to be, what the trajectories were. So we got a team that did what we called the Automotive Competitive Study. So we looked at this and we said, okay, kind of asymptotic analysis. Where does the technology need to go? What are the enablers to get it there? And we developed from that point forward, that kind of instructed the work to do what we call Gen 1. So Gen 1 was this very compact system. It looked like a line Ford gasoline engine that would easily fit under hood. The reason we had it in the Equinox then was it took an Equinox to house that original Gen 0, but we actually had Gen 1, so they would package under a small sedan, engine compartment, things like that. So
it was early 2000s time frame.
So this was around 2008, 2009-ish time frame, and we started to get that kind of a system put together. We cut the platinum level in half. We made some directional changes in terms of the design. So getting away from those carbon fiber or carbon composite plates where they were very thick. So the repeating distance on the stack was very long, so you get tall stacks. So if you went to a stamped metallic plate, borrowing from the automotive industry experience on things like head gaskets, right? We know how to make a lot of head gaskets and do them economically. So we got to these bipolar plates that could be stamped. And so that took the cost down, that took the packaging down. It made it much more reasonable to move forward. And we simplified the mechanization of the overall system. So the number of sensors, the number of valves, all those things, and borrowed from the parts bins of things that are more automotive in nature. And that simplified the design. And then, because what you said, we had millions and millions of miles on that Equinox fleet. We spent that time with that fleet not just accumulating a lot of miles, but we developed the analytical models that let us model exactly how those vehicles were operating in the field. So when we went to Gen 1, we didn't need another 100 and something vehicles out there to go and prove out what it would do. We validated the models in the lab. We could prove how that would operate on the vehicle. So we kind of went down that road to lab to math, virtual modeling pathway. And that was incredibly enabling. And so with that, we learned even faster. So to your point, we accelerated the learning periods. And we also learned in the laboratory how to accelerate the durability testing. I mean, you can imagine if you're developing these high mileage systems, and if we start talking about replacing diesels, you have to get to very high miles. Yeah. So you want to get to a 30,000 hour system. You're not trying to deal with something that lasts 1,000 or 2,000 hours.
Million-mile durability.
Million-mile durability is where you have to start heading. And so you have to be able to test these to prove everything out, and you have to do it with acceleration tests. That's not anything that existed in the testing methodology.
So that was a big leap.
That was a big leap. Yeah, we had to do that. And so now we have those accelerations. And we can put those acceleration factors into our testing. And all of what we launched yesterday, the Gen 2 system, has been down using those models. We took what we learned in the Gen 1. We took what Honda brought to the team. We had number 1 and number 2 in the patent space when we started our joint collaboration.
They came in 2013. 13, right?
Yep. And then all of that together, we started kind of building this out. And in parallel, we had to kind of develop some of these applications, because I think the first place that this is going to make the most sense, where it's really economically paying off for the users, is going to be in the largest vehicles first. And
long-haul trucking.
Long-haul trucking, if you're talking about road applications, big mine haul trucks, if you talk about off-road. So we're working with Komatsu, and that's the 930E 320-ton dump truck. Looks like a Tonka truck, right?
The size of this room.
Oh, it's incredible. You take a ladder to get up to it, up to the cab. So it's 2 megawatts of power to move this thing, right? So it's a massive vehicle.
It's a big battery. If you're going to put a battery in it, right?
That's the problem, right? You see, batteries are great. Don't ever think that because I'm a fuel cell person, I'm not a battery person. I think batteries have a role to play. They're very important, okay? But I think the fuel cells and the batteries are complements to each other. Yeah. And if you're trying to solve all the problems with a battery, you're handcuffing yourself, because the largest of the vehicles need the energy storage density that you can get out of hydrogen, and you can't accomplish that with batteries. Even the most leading edge batteries, for those very long operating cycles with very heavy payloads and the need to refuel quickly, you need the hydrogen as the solution, and that's an order of magnitude less costly for putting the same amount of energy on board the vehicle. And so that's kind of where you step into with this. And that's, I think, where we had to do a lot of development to develop those new applications, because those industries weren't even looking at batteries to the level that we were doing in automotive. So we had to bring them along that pathway.
But Charlie, I'm wondering, you had John driving around LA in an Equinox. You had customers driving around in Equinoxes. So what was the sort of feedback you got, not from him, from regular people?
Yeah.
And B, you talk about these commercial applications, yet the base of information presumably is from regular folks. So how is this reconciled?
So that Project Driveway fleet, I love driving those cars. They were very, very, they seemed commercial. You had a hard time. You had to kind of remind yourself that those weren't production vehicles.
Were they badged? H2 or anything like that?
Well, they said they had it said hydrogen fuel cell on the back. There was a badge.
The most remarkable thing about them is that they were completely unremarkable.
I think that's the right way to think of it. That is exactly the right way. My favorite thing about it was actually the shutdown. So that was different because we would purge the system of all the water, because you didn't know if you were in Alaska and it would be freezing and things like that. So we'd blow out all the water, and so you'd shut it down and you walk around to the back and you just hear it make these very characteristic sounds as it's flushing the water out of the system.
Explain where the water comes from, though. I mean, we're assuming that everybody knows how fuel cells work.
Yeah, so hydrogen is used as the fuel. It's the energy carrier for a fuel cell. So we bring that in, that goes into one side of the fuel cell. And then on the other side, we take air right out, we just compress the air and we put that in on the other side. So what happens is in a fuel cell, there's a membrane with an electrode on both sides of it. And the one side where the hydrogen is, the catalyst breaks the diatomic hydrogen, which is 2 atoms in the molecule, breaks them apart and separates the proton from the electron. The proton wants to complete its charge balance and
wants to rejoin with
rejoin, and it can actually get drawn through this membrane. The electron won't, right? So the electron will make the trip around to join it on the other side. What the proton wants to do is get to the oxygen on the other side, which goes through another catalytic reaction, breaks that diatomic molecule apart. So you've got 2 oxygens ready to then go and combine with the hydrogen. So you basically get H2O, water, and you've completed the electrical circuit because you need those electrons to make that reaction happen. When they come around to the other side, they've done the work through a motor or whatever else you're trying to power, and your waste product is water. So that's kind of what makes them so magical, right? Is you're just putting 2 gases in, you can't even see them, and you're making electricity, and you're doing it with efficiency in the 60-65% range, and you're making water as your exhaust product. So when we have these going into freeze, we flush that all out because water could freeze, and you don't want water collecting in different mechanical parts of the system. So you just blow it out the end of the tailpipe. And it was great because it actually had a unique tailpipe. It was kind of segmented, and you'd watch this steam coming out the back and made these great sounds. And so I think that was really kind of the fun part of it. There were a lot of customers that when it came time for them to turn these cars back in, I mean, we had to pry the keys out of their hands because they were just religious followers of, they wanted to buy the next hydrogen fuel cell. And unfortunately, those Equinox vehicles, as great as they were, they were still expensive, and they were designed to be a development fleet. They weren't really designed to be a production feasible vehicle at that time. And so we had a lot of work to do to bring the costs down. And now with the Gen 2s, we've gotten down to, we're in the range of a quarter of that precious metal
Tell us
loading.
more about that Gen 2. Size, how big is this thing? What have you done with the Platinum? All that kind of stuff.
So the Platinum is about a quarter of the level that we were at. And so I
think you're talking 20 grams of Platinum?
It's in that range, yeah. So it's much less, and we've got the membranes are now made at very high volumes, as we indicated before. These plates, because they're thin metal stampings, we can basically get a very compact stack. So the stack itself is, yay big, with the parts around it to go in and basically make it work. So you've got a big compressor. It looks like a turbocharger, actually. And so it's taking some energy that's out of the waste, and it's using that to help compress what's coming in, but it's electrically driven. So we drive the air through with basically a big compressor, and that compresses the air side of the stack. And then we have injectors that are injecting the hydrogen into the system, and those have some proprietary designs that GM has invented, which in the past, there were different types of things like recirculation pumps and hydrogen pumps, different things that were used. But what we found was we could actually simplify the system and use an injector with a venturi that would cause the mixing of the gases and make everything function that way. And it looks kind of like what you might have with natural gas injection systems, if you want to think about it that way. So that's where we started leaning on the parts bins that were out there for automotive and put that in. And then there's coolant. And you can't underestimate the coolant on a fuel cell system, because an engine wastes most of its heat through the exhaust. Almost all of our heat rejection comes through the coolant. We have very little coming out the exhaust, and we're higher efficiency coming out in terms of useful work. So what we have to have is good cooling. And because it's coming out so low temperature, it's going to be operating up to maybe 95 degrees C. Because of that, that means you've got very low-grade heat. So you need a radiator that's sized to be able to deal with that. And that's part of the development that goes into putting these into the different vehicles.
Heat is generated just from the electrical reaction in the cell?
Yes, exactly.
Mhm.
Yep. So we keep it cool. It likes to be cool. It likes to be humid, which it makes its own humidity. But we actually have something that's a lot like, if you remember when we've talked about diesels in the past, and EGR, exhaust gas recirculation, was a big thing. Complicated, right? Because you have to run the exhaust through to dilute the combustion mixture and bring the emissions down, and then you'd cool it and do different things. We kind of do something like that on a fuel cell, but it's the humidifier. So we take some of the water that's coming out, and when you run through this compression system for the air, you get some pretty dry air coming into the stack. So we want to humidify it again. So we'll use that water coming out the back side of the tailpipe, basically, before it gets there, and we'll recirculate that back into the system through a humidifier. So it's kind of like an EGR system on an engine.
What level of humidity is that at peak?
It depends on where you are in the cycle, but we run very wet. In some cases, we're actually to the point where we're developing liquid water in the system.
And you had mentioned early problems. I remember driving an Opel Zafira in Germany back in maybe early 2000s. And your engineers had said before you were on the program that the cold weather operation challenge was pretty much taken care of at that point. Yeah. So there's no worry about, if I live in Bemidji, Minnesota, of buying a fuel cell autocar truck. And
no. That's a good point, because what we've done is we've targeted something that could truly be a replacement for traditional propulsion systems. And we all know where diesels are used. I mean, they're used in the North Bank in Alaska. They're doing work everywhere. And so we couldn't have a system that was going to be compromised that way. So our systems are designed, they work reliably to start down at minus 40. They'll work up to, positive 40 degrees C. So we're in a range there.
Automotive thermal range.
That's exactly how we designed the system.
How about cost? I mean, I'm not expecting you to give us strict cost numbers, but where do you stand now versus batteries with the battery electric? Where do you stand against
a
diesel engine right now? Do you see a pathway to get under them?
Well, it's still more expensive than a diesel engine today because we're not in the high volume that diesel engines are in, and it is a scale business, and so we have to try to compare on comparable scale if you really want to do a fair comparison on cost. But with the way that the precious metals have been coming down, with the way that we've been optimizing some of the other things like getting away from these carbon composite plates and getting to the stamp plates, that's lent itself very well to being more economical and getting to where we can challenge diesels in some applications. Now, it's not going to be the right solution from a cost basis everywhere. It's basically a total cost of ownership model that you have to think about. And we pick up advantages in terms of efficiency. You have to look at what the cost of the hydrogen is that's being used, because sometimes the hydrogen is going to be pretty economical. Sometimes you're leaning on limited supplies in an area and the hydrogen cost goes up. But the idea that you move toward an electrified solution where the wheels are turning constantly, earning money, like a mining truck, that's where you can really start to shine. And so that's how we're focusing on this going forward. I think in time, the cost of internal combustion engines and meeting the emission standards that are increasingly more challenging, the after-treatment systems that are in there, some of those after-treatment systems in a diesel are using almost as much precious metal as we have in the fuel cell stack. Different metals sometimes. It could be palladium more than platinum and things like that, but it's still thousands of dollars that you can put in for after treatment costs, and that's giving you some headroom in terms of where you can find the comparable fuel cell system that can compete with it. And so I think going forward, we'll be able to compete with those diesels. And there are examples today where the propulsion system of choice from the lowest cost solution ends up being a fuel cell. And the best thing to look at is forklifts. They're probably the most forklifts that are out there fuel cells that are out there in the US right now are hydrogen powered. If you think about it, in the new high capacity plants where they're running 3 shifts, they don't have time for battery rooms and battery changes and putting these things on for quick charges in between shift changes. So that's where you can really get in and change things. And they're already paying for themselves. They're pulling lithium-ion batteries out. They're putting hydrogen fuel cells in, and that's where it's all driven by economics.
I think it's worth.
Yeah.
I think it's worth pointing out to the audience that you started out as a diesel guy. So when you're talking about diesels, this isn't like, like, oh, I'm a fuel cell guy, therefore diesels are, not as good. I mean, so you have deep knowledge of that. Talk a
I
little bit
started
about
my whole
that.
career in diesel engines. So it's kind of ironic that today my job is to try to replace the engines that I spent all my time trying to develop, whether it was all the way back to the Detroit diesel days or when I arrived at GM and it was, God, what a gift to be able to work on the Duramax diesel. I mean, that was taking that engine through its generations and emissionizing it and working with the team that was doing that. I mean, that was my dream. I mean, I thought at that point my career had gotten as far as it had to go because I had gotten to what I always wanted to do, is work on those really high volume engines that make a difference. And then along came the fuel cell. So yeah, it was kind of a little detour, and then it became the second half of my career, basically.
Charlie, to John's point about cost, looking at some metrics of cost per kilogram of, say, gaseous hydrogen versus a gallon of diesel fuel, cost of other aspects of the engine, and also performance metrics as well, specific output and so forth, versus like the standard inline six Cummins diesel that would be in one of those autocar refuse trucks. Where does your system stand right now?
Yeah, so hydrogen today is more costly because of how we're distributing it, how it's being dispensed, things like that. So 1 gallon of gasoline or diesel fuel is about this. You can think of it just round numbers. It's about the same amount of energy as a kilogram of hydrogen. So today, you're looking at gasoline that's sitting, in the $3 a gallon range, depending on what octane you're buying. Diesels fluctuates quite a bit, but it comes off of a different end of the distillation tower. But usually it's going to be somewhere in that range. Let's just round off. I mean, the last couple of years we've had some above gasoline, sometimes dropping below. But if you just kind of say this $3 window is about where petroleum prices are, that means that the hydrogen cost needs to get down for parity. It's got to be within twice that number because we're about twice as efficient on an overall propulsion basis. And so if I'm sitting at $3 a gallon, that means that my hydrogen should be in the $6 a kilogram range.
And right now, my understanding is it's in the $13 to $15 a kilogram area.
So if you go to California, where it's a very nascent infrastructure, there aren't a lot of stations. I think the number right now is about 62 or 65, something like that. And they're very low utilization rate. I mean, those stations might fuel one vehicle a week sometimes, right? Hard to make a business out of that. And so you put in a big station fully capable of maybe doing 1,000 cars and it's fueling one, right? So that's not a very practical business model. So that naturally runs up the cost of your dispensed hydrogen. But that's not the way we should be thinking of the business, right? I mean, if you're going to do this, you're going to do it at scale. Partly why we're picking these very large vehicles as one of the starting points for the business is because they tend to operate in centrally refueled locations. So if you're at a mine, all the trucks would refuel at the same point. So you can size that infrastructure around what the fleet demands and keep it fully utilized. And that allows you to bring the cost down. So price of actually producing the hydrogen is, now you're well below $1 to make hydrogen. It's a matter of storing it and compressing it and cooling it and distributing it and all the other things that go along. That's what runs the cost up. And getting the return on your capital to put the stations in drives it up. So we're trying to focus on these ways that we don't have to go and bite that one off at the beginning. We can start to tackle it in pieces. And I actually think it's going to roll out something like the diesel again. So when I started working on diesels for automotive, nobody thought you were going to have automotive diesels in pickup trucks. I mean, that was viewed as, why would anybody do that? And one of the biggest excuses was nobody will want to go to the truck stops to refuel those pickup trucks. But the propulsion system was so fantastic that people were willing to make that compromise. They'd go to the truck stop, they'd fuel up, and that got more vehicles on the road. And as more and more vehicles came to the road, then you could justify pretty much every Meyer and I fuel up at Meyer or BP stations quite frequently. They're all there with hydrogen, or I mean, not hydrogen, diesel pumps. They will be with hydrogen pumps. They will be there with hydrogen pumps. So that's, that's all there. And I think that's where this is going to start to go in the future. You'll start with these big trucks going out. They'll be using the centralized refueling, and eventually over time, as more and more vehicles are out there, it can start to distribute into the smaller.
Okay, wait. We're going to take a quick commercial break right now. We're going to give a shout out to our sponsor. We'll come back to it.
How do Bridgestone tires stop shorter on wet roads? It's their HydroTrack technology. But you don't have to know how the science works, just where the brake is. What really matters is their Bridgestone.
Talking hydrogen fuel cells with Charlie Freese from General Motors. And I know the way the conversation's going, we are going to run out of time before we run out of questions. Lindsay, back at it.
Real quick. Okay. So scaling up this hydrogen distribution availability. So you've got users like a mine having their own distribution for the trucks and equipment that's being used there. Last year, I believe it was, the government established these hydrogen hubs, nationwide kind of regional hubs. You must be excited about that in terms of another piece of the puzzle kind of coming into this.
Yeah, I think hydrogen hubs are going to be an enabler as long as they start up in the places that are close enough to these different big users so they can get the volume, the throughput. There's a lot of hydrogen in the country right now. It's used to fluff gasoline in the process at the refineries. It's used in making fertilizers. It's used in steel production. It's
used to hydrogenate peanut butter.
It is.
It exists in nature too, by the way.
Exactly. So it's there, right? What this is going to do is it's going to put some big volume distribution networks with kind of a hub and spoke. Mm-hmm. And as that starts to roll out and you start to build fleets around that, I think that will help things substantially. But it alone probably isn't going to fix the whole challenge. I think what you're going to have to imagine here is starting to leverage nodes. And let me kind of describe that here. If you start to think about forklift fleets, which are already using hydrogen, and they're at warehouses and factories, so there's already a refueling site there. If you imagine all the other things that could leverage that same investment in hydrogen refueling, and it's going to start with the vehicles that come into and out of the factories and the warehouses. And so these are trucks. So that's why we work with a company like Autocar to develop Class 8 trucks, because they can start to leverage that, not only making it more efficient putting the hydrogen there for the forklift fleet, but also for those trucks. The other place the trucks go is they go to ports, they go to airports, they go to rail yards. And so then you can start to make another node, right? So at those airports, the aircraft, which we're working with Liebherr Aerospace right now to put hydrogen fuel cells into commercial aircraft, and they would leverage that same investment in the refueling. And the trucks that come into the airports can also refuel there and leverage that same investment. You can also think of it as a rail yard solution or terminal tractors at a shipping port, and that's another thing that Autocar develops. So I think that smart collaboration between different industries and trying to find ways to maximize the efficiency of the investments, that's the way this thing can start to roll out.
So Charlie, if we look at the scene right now, so Toyota's working with Peterbilt in terms of putting fuel cells in there. Hyundai's got its own Class 7, I don't think it's a Class 8 truck, but be that as it may, for all practical purposes, a long haul. Honda is going to be testing a fuel cell in Japan, and then they said they're going to be bringing it here 24 or 25 for testing. You guys working with Autocar, I mean, do you see that it's this trucking more than it is, a fuel cell Toyota Mirai that's going to be making the difference in terms of building this out in a big way?
Yeah, well, I think it's obvious. If you just watch what all the participants in the industry are doing, everybody's trying to focus on Class 8 trucks as one of the segments because it does make sense. And it's also a place where if you're hauling heavy payloads, so liquids, steel, I mean, the things these trucks are best at, you need that energy storage density that comes from hydrogen. If you're hauling half-empty Amazon boxes, it's maybe not a big deal. Maybe you can even deal with using batteries. And some companies are trying that. They're trying to put batteries in for local distribution, things like that. That might be completely viable. But
Hauling potato chips.
Potato chips are a great example. But if you want to haul the heavy stuff, which is really what these trucks are best at, then that's where you're going to bring in the hydrogen. So I think you're seeing that segment already. I don't want to speak to a specific competitor or anything like that, but I can tell you from our perspective, starting in those small vehicles doesn't make sense. In our portfolio, we have battery technology that can serve those needs and do it very well. So if you want to electrify a passenger vehicle, then a small passenger vehicle like your everyday driver, then you have a solution with batteries. Most of the time, those vehicles are stopped at either your home or the place of work or some other location for an extended period of time. They're not on the road most of the time. And so that gives you the time to recharge them. And that's completely viable.
What about fuel cell as a range extender? You know, Stellantis is talking about that for its full-size pickups, which I find intriguing.
So a fuel cell as a range extender, you might recall when we introduced the Volt with a V, that was a flexible architecture that had engines, or it had a fuel cell variant, different ways that we configure that. So you can do that. But the thing you got to imagine is one of the challenges is to put the energy on board the vehicle and manage not just the energy you put in when you fuel, but the energy that comes to or leaves the vehicle on an operating cycle. So what I mean by that is if I'm putting a big heavy payload out there on a vehicle, it's got to go up the hill and it's got to come back down the hill. And what I want to do is I want to bring it down the hill and capture all that energy coming down the other side of the mountain. I don't want to give that up in terms of brake heat, because I've already electrified the overall propulsion system. So anything that doesn't capture that is wasteful. And I've got a very capable propulsion system. And if I don't size the battery right, I can't actually do that, right? So the challenge is going to be how you keep this battery right-sized and not have it become so big that it jeopardizes the payload of these payload-carrying vehicles. And so that's all where the battery architecture comes in. So I would say that different configurations might make sense for different types of usage cycles. But the thing you're always going to come back to is how much energy do you need to be able to capture from that braking? That's going to very often size the battery. And once I've sized the battery, then the question is going to be how much fuel cell and how much hydrogen do I need to do the rest of the cycle, get it up the mountain as well. And so sometimes you might be able to think about that, but we've actually found the optimum solution looks a lot like a hybrid where the engine is pulled out and the fuel cells put in its replacement.
So, for example, in a fuel cell powered Class 8 road tractor versus a battery electric Class 8 road tractor, would your storage battery be, say, 50% the size of a BEV?
It's going to depend on the cycle. Okay, and so if you're doing a cross-country haul, right, you're going to probably be going over some mountains. And if you're hauling heavy things, you're going to make a lot of energy recovery as an opportunity coming down the mountainside. So those would be very large batteries. The fuel cell in these trucks is going to be about 300 kilowatts.
In these refuse truck, the autocar application.
In autocar, but that's a different load cycle. So autocar is an interesting one because these vocational vehicles, it's not just moving the load, it's operating all the equipment on the truck while the load is either stationary or in movement. So if I'm talking about a cement truck, I've got a big drum of cement that is constantly mixing, right? Yep. So I'm moving the heavy load, but I'm also mixing the cement. And that uses a lot of power. If you imagine a garbage truck, right? So a garbage truck has the compactor on there, and that's using a lot of exportable power off of the propulsion system to do that compression of the refuse in the garbage truck. So you have to be able to think about the overall cycle. We actually are very excited about what a fuel cell can offer that way, because we not only give high range for a vehicle, but we can give extended operation when the vehicle is on a job site trying to do work, even exporting power off the vehicle. And we did that with the Equinox. We had operating job sites where we basically had an exportable power unit on the back, and we could power contractor tools and circular saws and things like that. When we had the fleet at it was at one of the military bases in Hawaii, and they were doing some testing with that fleet. And we ran the entire dedication ceremony off of the Equinox quietly. Nobody even knew it was running, and it's sitting there running all the lights and the microphones and everything.
So are your colleagues at GM Defense really interested in fuel cells?
So we are working with our GM Defense partners. We have a number, if you might recall, a few years ago, the ZH2. So the Colorado ZH2 was the very first vehicle that we did after the Equinox. So
we drove that out at Milford, I think.
Yeah,
that was a demo.
Yeah, that vehicle was a lot of fun to drive, because I mean, I come from off-road motorcycle roots, right? So my dad had a motorcycle shop, and I drive motocross bikes, and that thing, we got that thing airborne sometimes. I mean, it was an amazing vehicle that the military, they were rough on it, you know, and it did all kinds of things, but that vehicle had this exportable power, and that was kind of what set the stage for some of the collaboration on the GM Defense side. So the military, they're learning kind of what it takes to do some of the things that they want to do, and they're evaluating these different technologies. And what you find is, as you start putting more and more electrification into the field, you can open up all sorts of other benefits. So that Equinox had a very low thermal signature. It didn't have any sound to speak of from any distance, which is very different than a generator. I mean, if you look at the generators just think of your own neighborhood. If the power goes out, you can hear your neighbor's generator from, you know, blocks away. And if you're trying to be stealthy in a battlefield situation, the last thing you want is to be having a noisy generator to power your recharging for battery vehicles or whatever you're doing, your comm systems and other things. So they were quite interested in the concepts that we could offer by providing exportable power off of a fuel cell system that operates quietly, but it also, because of that low thermal signature, you don't see it on thermal imaging. You don't smell it. You don't see the smoke. They actually, with some of the vehicles that they operate, the way you find them is you look for the smoke. And so we were testing that ZH2 out in Fort Carson, and they always told this story about how they did a night operation, and they basically took the soldiers and they put them out on this one ridge, and they told them to set up an encampment. And there's a hill going up to it. They called it Agony. So this is like every vehicle going up this thing is just roaring along, right? So they set up the encampment, and the mission was to go in for one team to go in and basically invade the other team. And so they sat up there, and the next morning after this was all over, they said, "You never came." They said, "We were there." They showed how close they got. They left. They came back again. They left. And so it was all just because the ZH2 was able to go up quietly. It didn't make a thermal signature. There was no smell from diesel exhaust. There was no noise. I mean, it was game changer. And it's also kind of interesting. You can make your water in theater, right? Mm-hmm. So the other thing they carry is a lot of water, and that you can make your water in use.
All right. Is this potable water, or is this water that you're going to use?
Don't drink it. Don't drink it. Yeah, you've got to, because it's basically coming out as deionized water. And so, you know, if you drink deionized water, you could get sick. So you'd have to add some things, to add some minerals so that you could actually make it potable water. But that's much easier than trying to find other water sources in a desert or something like that.
Charlie, in this long development journey that GM's had, you've brought the supply chain along, which didn't exist in this realm before. I'm curious, your current technology, what rough percent of suppliers are traditional automotive suppliers, and what percentage are new startups or new hydrogen tech segment suppliers? And what are you looking for? I know some of John's audience are supply guys. What are you still looking for in terms of supplier technology?
Yeah, so that's a great question, Lindsay. Are you thinking on a per dollar basis or on a part count basis?
Well, just a bill of material basis.
Okay, so I would say we're probably leaning about half and half.
Wow.
There are a lot of materials and suppliers that we had to go to that just aren't big players in some parts. I mean, if you think about the things that you're doing on the membrane, that material, there's
coatings and so forth.
Yeah, there's some companies out there that aren't traditional. Now there are others that have started to get into it and have been involved in it in various development ways over the years. They might be the companies that are doing after treatment systems for diesel engines, as an example. And so that's one. But there's some companies that have done carbon fiber in automotive, but they haven't really been in propulsion systems. And so a lot of what we're doing now is relying on carbon fiber. That's a big one.
Tanks, particularly, right?
Tanks is a big part of it, but we also there's a layer that goes into making the membrane electrode assembly that goes into every cell, and it's actually hydroentangled carbon fiber filaments that change the distribution of the water that goes through the system, right? Yeah. So we call that the gas diffusion membrane, and it's changing the way the water moves, the way the gases move, and making sure that they're evenly distributed across the cell. So that's not something that is, quite like what you would normally do in an engine development program or something like that. So we had to develop some of those kinds of suppliers into that space. There's a lot of things like the valves. These are valves that are dealing with a lot of water, and that's not necessarily it's not like a coolant system which has antifreeze in it and that kind of thing. I mean, these might be dealing with water like drain valves that are taking the water that develops in the stack and purging it at certain cycles and things like that. So those are new suppliers.
They're bespoke for these applications.
Some of them are, yeah, and some of the way we do the ends of the stack, those kinds of parts are somewhat unique, and then there's all the safety systems that you put into a system like this, because we're dealing with hydrogen, we're dealing with electricity. The vehicles might crash, and so you have to be able to discharge all this energy safely very quickly. The parts that go into that, pyro switches and things like that kind of borrows from airbags, but they've never been used in these kinds of configurations before in an engine, let's say. So different things that we had to kind of borrow from. So I think going forward, we're always looking for very capable automotive type suppliers that are willing to take what they know, because what we're finding is there is a lot of overlap. There should be a lot of overlap with the traditional automotive supply base and their know-how and where we need to go with this. When you talk about a casting, I mean, a casting is a casting, right? And so we have aluminum castings in this that are doing the housing around the stack. And so getting aluminum castings or cradles that hold the unit, which look like an engine cradle, but sometimes they're different. It's a little bit different designs than people are used to. And so we've got to do a little bit of development with the supply base on
So
that.
what you're saying, so if volumes really take off, some of these little specialist guys will have to be brought into a higher volume realm.
Or some of the large volume suppliers will maybe step into some of those areas. Yeah.
Hey, we asked our viewers to submit questions, and I'd love to go through. We're not going to get through all of them. We've got so many here, but I'd like to go through rapid fire style here. So we'll need short answers. So Robert Parent from Winnipeg, Manitoba, wants to know: do you think that fuel cells are going to go through the same infrastructure issues that the EV charging part of it has gone through?
Well, any new infrastructure is a challenge, and there will be some fits and starts, I'm sure. The trick, kind of as we talked about, is how you get through this transition phase and get the volume up to enough that it can sustain the scale that's needed to bring some of the costs down. But I mean, we've done some analysis work, and it takes basically the same investment to put in a coast-to-coast hydrogen infrastructure on a cost basis as it does for coast-to-coast on charging. So it's doable.
Is the hydrogen highway still under construction in California? The Schwarzenegger plan, remember?
I think they've located a lot of their stations up along that highway, but I don't know that it was actually finished to the way it was envisioned.
Okay, we've got another question from Chris Gippsland from Australia, and another one, Christoph 1888, very similar. What about running fuel cells on alcohols, propane or methane? Would that be viable?
Yeah.
And what are the main issues?
Yeah, so there are a lot of different fuel cell configurations, right? I mean, there's methanol fueled fuel cells. There's different types of fuel cells. For the business that we're in, we found that the PEM technology that we have and fueling off of the compressed hydrogen seems to be the pathway to get us to the best solution for the customers and the usage cycles that we're trying to solve.
Okay, Todd Crook from Long Beach, California says he drove a Honda Clarity Fuel Cell 3 for 3 years, put 60,000 miles on it. He would love a plug-in fuel cell. Now, Honda's going to do that, excuse me, with the CRV one, right? What do you think of that, of
Perfect
being
sense.
able to plug in when hydrogen's not available?
Yeah, every fuel cell should have a plug on it too, because why not, right? I mean, the electricity coming off the grid is quite inexpensive. And if I ever am in a situation where I am constrained on whether the hydrogen network has been built out, I can still probably do plenty with a plug that plugs into the wall. So it's a great way to augment the vehicle. Most of the hardware is on vehicle anyway.
Stuart Midwinter says, what's the overall efficiency of a fuel cell EV versus an ICE vehicle?
So an ICE vehicle is going to sit somewhere in the 30% range, right? Depending on how much it had to have as emissions or curtailment to that sometimes. A fuel cell will be up in the 65% range. So the best way to think about it is we're about twice the efficiency.
Okay. Kay Sermon, I hope I said that right. He says, who's going to be responsible for all this hydrogen distribution? And he also wants to know, what about the hydrogen brittleness on steel parts?
Yeah. So, okay.
Two questions.
here.
Yeah.
So as far as who's responsible, I think this is going to be, there are already companies out there that are taking advantage of a market that is developing for hydrogen supply and distribution. And I mean, a perfect example is the forklifts, right? There are companies that's their business. To get that hydrogen there, they make money at it. They're profitable. So there will be companies stepping into the space. The trick is coordination. And I think there's got to be some industry coordination. OEMs need to coordinate. The supply industry needs to coordinate. All of that's got to happen, and then eventually, if we can manage this right, we can be visible enough about how these different examples of production equipment are coming out in the marketplace, and people can plan the infrastructure around it, because they all have to kind of match. As far as the embrittlement, that's completely manageable. I mean, we obviously wouldn't be putting fuel cells together that are going through the
You talked about steel stampings, right?
Yeah. So that's manageable, and I mean, even in pipelines, there was a big thing about hydrogen embrittlement in pipelines, and they're already blending hydrogen into existing pipelines because they're mixing it with natural gas, methane, and they're using that as a distribution. It's happening in Hawaii quite extensively, and embrittlement's not a problem on that.
So Data Matters 8 says there is all kinds of R&D money pouring into battery electric vehicles, batteries especially. Can fuel cells keep up in terms of all the R&D?
Yeah. Well, I don't think it's a competition that way. I mean, yeah, there's always a challenge that you have a lot of things to develop, and it can be expensive, but I see these two as complementary. A fuel cell will make a battery electric version better for these big vehicles, and a better battery will make my fuel cell more efficient as a propulsion system. The two need to go together. And honestly, we've had a lot of learning that's come out of some of the things like what we've done on fuel cell development. When we started really ramping up batteries in GM, we took a lot of those fuel cell engineers and put them into the battery space to make sure that learning carried over. So I see them as actually complementary in the development as well as in the product execution.
Mm-hmm. And Shakas wants to know, is green hydrogen 5 to 6 times more than efficient than electricity? I must have written this down wrong.
Maybe more expensive.
Yeah. So that's a good question. It's hard to answer quickly. So, I mean, really, one of the reasons green hydrogen is more expensive is because those green sources that go online are not leveraged to the maximum extent possible. And that's because they're cyclical, right? So wind doesn't blow continuously. The sun doesn't shine 24 hours a day. So what you end up with is mismatches between the production of the green energy, the availability of the source, and the demand on the grid. And that's very hard to manage on the grid right now. So what you end up doing is you put in a wind farm, and when you don't have a use for what's coming off the wind farm, you stall those wind turbines, and you've just got a very expensive investment that's doing nothing for you. You're wasting the energy. Hydrogen is the solution, right? So hydrogen, I can take that energy off when I don't have another place to put it. I can store it for long periods of time if necessary in the form of hydrogen. It is the buffer for the green energy grid when that develops.
So basically, electricity is being generated to use electricity to do electrolysis, break water apart, get the hydrogen, put the hydrogen in the tank.
And that's exactly why we're working with Nel on developing lower cost, more efficient electrolyzers using the very technology that we've been developing on the Hydrotech fuel cell systems.
Where does that stand right now with Nell's development of that?
Yeah, so Nel and GM are working on a joint development presently, and we're taking all that technology that's coming out of those PEM fuel cells and applying it to their electrolyzers so that we can help them get to scale, bring the cost down. They're installing the equipment will come into a plant here in Michigan, not too far from actually our lab up in Pontiac, so that we're able to share the learnings between the two, and we're quite optimistic about how that's developing and where it'll go.
You know, we had a lot of viewers write in very skeptical about fuel cells in light vehicles.
There's always a few.
but you're saying you don't really see it going into light vehicles. That's not where you see the sweet spot for fuel cells.
Not small vehicles. I mean, I think in you know, our leadership in GM have said that we will have in our portfolio a fuel cell solution, right? But it's not going to start in the small cars. It's going to have to come from the top down, and that's really the strategy that we're on. We don't want to put a technology into a place where it takes away what the customers want from their vehicles. We need to add more. We always need to be able to find a way to solve problems and give them more, and that's really the focus on how we're developing the technology.
So what you've said is fuel cells or forklifts make a lot of sense. Long haul trucking makes a lot of sense. Generators, I mean,
generators.
What
Yeah.
about home generators? I would love a fuel cell generator as a backup supply for my house.
Yeah. So for generators, I think, you know, some states are actually prohibiting internal combustion engines as a generator solution. Some of the permitting to get those kinds of installations in is very lengthy. So I think hydrogen and fuel cells can be an enabler to unlock some of that and make that happen going forward. But the thing that we're finding very interesting is these mobile generators, right? So we've got some Hydrotech power units that we put together. It's basically, think of it as a trailer that has 2 fuel cells on it, sometimes 1, depending on how we configure. It might carry its onboard hydrogen with it. It'll have 1 or 2 chargers on the back. And so if you're going to go out to the middle of the desert where there is no infrastructure for anything, you can take that out there, park it there. And if you want to take Hummers with EVs and run them all day in fleets, actually some of the vehicle evaluation teams that have gone out and compared competitors, they've actually borrowed those units from us so that they can keep like an all EV SUV fleet that's out in the middle of nowhere charged and do it quickly. So DC fast charging, very fast. And hydrogen can provide that where you're not going to get there with anything else unless you want to run a diesel generator to try to charge these vehicles.
And you had said something about planes?
Planes are an interesting one. That's a longer time horizon because you don't just do a new airframe in commercial aircraft every year or every 4 years like Automotive.
747s are still in the air, and they were started when I was in high school.
Yeah. So what happens is we have to be in early in it, which is why we're working with Liebherr Aerospace. And the first best step into that space is going to be by replacing the turbine that's at the back of the plane. That's the auxiliary power unit. And that's there to make electricity for the aircraft, whether it's sitting at the terminal or whether it's in the air. And that's hard to optimize a power generation system so it works just as well at altitude as it does at ground level. And it's very noisy. It emits a lot of odor. It's smoky. You see all the baggage handlers with noise protection. When you get on the jetway, right, crossing over, that's the thing you hear screaming away at the back of the aircraft so they can keep the temperature correct and keep the lights going in the aircraft. And so that's the place we're going to start. We'll go into that application. Liebherr's working with us to get the solution using all the Hydrotech technology. And then when you replace that turbine in the back, I can get a more efficient solution. I can use the waste product for water to either humidify the passenger compartment or maybe flush toilets. A big commercial aircraft has about 2 tons of water to flush toilets. That's a lot of mass to take off with. We can make water in flight. So you can start to go and change the architecture of the aircraft piece by piece. It's also interesting because a commercial aircraft is very predictable, right? It's not going to stop en route and decide to fuel at some unpredictable place. It's going to stop at an airport. And so you can put the hydrogen at the airport, support not only the vehicle, but the ground support equipment as well, which looks a lot like a forklift, by the way. So you can start to optimize that, and you can design it so they take off full and they land as close to empty as they can get. that actually works for liquid hydrogen, which now I can start to put even more density in my energy storage, and it's a whole game changer. And we're actually looking at the same thing with the mining equipment, because they can actually justify putting liquid hydrogen on board those vehicles so they can extend the operation between refueling at the mine site.
When
How
you're
about
liquid,
trains? How about trains?
Trains could do the same thing. Yep. And you might have a tender behind the vehicle, the first locomotive, and it might just be carrying liquid hydrogen. And again, it's predictable routes. It's knowing exactly how they're going to run, where they're going to run, where they're going to refuel.
So we haven't talked.
an electromotive division. You'd have a captive application for this.
Yeah, that was before my time.
That was a long time
That was
ago,
before
right?
my time.
So one of the things we haven't talked about, and I'm sure that people are wondering about, is safety of hydrogen. I mean, it may be a naive thing to ask about, but I've got to ask it.
No, I get that question all the time, and I'll know my job is done explaining hydrogen when everybody comes to me and tells me, "Oh yeah, hydrogen, of course it's safe." And so, I mean, hydrogen needs to be respected. It's a fuel. It's an energy storage mechanism, and when you deal with energy storage in dense ways, you always have to treat it with safety in mind, and we do that. So the thing I always like to refer to is when we were doing the work with the military. That was a big question in their mind, was how safe is hydrogen? Because they're not just trying to go and drive as an everyday driver. There are people that are shooting projectiles at these things. They've got to be safe under those conditions, not just an unexpected crash, but literally targeting the vehicle, trying to make it fail in a destructive way. RPGs. And so we did the testing with the Army. Actually did the testing. We supported them. They targeted the tanks with RPGs, with different rounds of incendiary rounds, with 5.56, 223. I mean, all these different rounds.
You're talking hydrogen tanks, not
Yep.
Army tanks.
Yep. And so they found that they were able to penetrate the tank. That's not surprising. If a rocket propelled grenade has its own explosives in the payload, it brings them to punch holes in things. So they would punch the hole in the tank, it would go through the tank wouldn't explode. I mean, I've got pictures that I like to show of the tank with the hole, and it's a nice little clean hole in, a nice clean hole out, but we didn't explode the tank. And that's what it's all about, right? Making sure that you've managed the energy that's on board, you've done it in a safe way. And so I think that there's actually a lot of benefits that if we were developing, if cars weren't on the road today and you said, how are you going to power these cars? Hydrogen would be one of the things you'd be talking about if you knew how to develop these different propulsion systems at the time. You'd be saying, wow, that's a nice safe alternative, because if it leaks, it goes up at about 40 miles an hour. It doesn't hang around. It doesn't pool on the ground. You have to have a combustion source to light it off at about the right stoichiometric mixtures, and it's easy to snuff itself out. If I had a leak on a tank, it ends up being more like a pilot light if it's lit off than something that leads to an explosion, because the mixture inside the tank actually couldn't go off. And one of the examples that we did was we actually took Mylar balloons and we put the perfect stoichiometric mixture inside the balloon with an ignition source in the balloon. So you can see through the balloon, you can see in there. You light this thing off, it goes poof, and it goes out. It puts itself out. The gas doesn't all go. The balloon doesn't pop. And it's because the pressure wave actually moves it to a non-stoichiometric mixture at the flame front, and you lose the combustion event, right? So it's actually you have to understand it. You have to manage it with safety in mind, but it's actually something that can be done in a safe way.
And hydrogen atoms love to escape just about everywhere. So is sealing technology finally nailed down? Charlie, in the units you're making, but also you're putting them in somebody else's vehicle, that's going to be really critical here, right?
Yeah, so we do know how to seal hydrogen, and there is no perfectly sealed device. I mean, everything has the ability to have leaks, but not in the area where it would cause these combustion events and things that you're describing there. It is kind of an interesting property of hydrogen, though, is that if you're running liquefied, which is what some of these applications are doing, that wouldn't actually work in your vehicle or mine, because if we go and park our vehicle at an airport for a week and we go on a trip, we don't want to come back and have vented all that hydrogen that was actually warming up and it was going to gaseous form. So that is one of the reasons we go to compressed hydrogen, because we can manage that. And it's actually high pressure. It's 10,000 PSI, 700 bar. We run the pressure to that level, but in that kind of form, in that kind of a situation, we can manage it and we can do it and contain it and do it safely.
Maybe one last question. What about making hydrogen on site? And I asked that because I remember when Larry Burns was running GM and R&D, he pointed out that every building that you look at, every single one you look at driving up and down the street has got water running into it. There's water pipes going into every building. And he said, man, if you could figure out how to make hydrogen with that water, you could make it right on site. Is there anything going on with that?
Yeah, so that is part of NEL, right? That's part of what we're doing with NEL. And that's a perfect way to think about it, John. I mean, the idea that the building has water, the building has electricity. Those are the two things you need to run an electrolyzer and make hydrogen out the other side. So I think that will, as the electrolyzer cost and efficiency improves, and we get to the point that you can make small or scalable units, you can start to get to where you can make your hydrogen close to the point you want to use it.
Could you do it at home?
Well,
Like having a home charger for your BEV, could you have a home electrolyzer?
Some
We're dreaming here, Charlie.
Some
I know, we're
companies have looked
dreaming.
at it. I will never say never. I just not right now. so I think, but in a scalable size to do a small fleet, this can start to make sense. And what I think is so interesting about it is hydrogen is hard to move if I don't have a pipeline, right? I have to do it in tanker trucks, and once you get over about 200 miles to tank it, then your costs go up and it becomes prohibitive, and you want to go to the next closest site. And so if you combine the fact that taking that distribution cost out of transportation, the storage that comes with it, and then the fact that if I leverage this green energy that they don't have a place to put it off the grid, I can start to envision a really interesting model of localized production, like you're saying, using electrolyzers close to where the fleets are refueling. And I think that's going to be something that, as the technology and the infrastructure evolve, we'll get to that point.
Can I ask one more?
Go ahead.
Okay, so in this whole challenge of bringing this to production, what is the greatest area of challenge? It sounds like you've got the vehicle, the hardware, the control systems pretty much nailed down. We talked about hydrogen hubs and distribution, and then there's this kind of overall goal of getting to a green hydrogen sourcing. What's the biggest overall kind of package challenge for this?
I get one thing.
Yeah.
One thing.
It's more than what?
Yeah. So one, I'd say, is coordinating that whole thing, right? I mean, because we have industries that need to provide the infrastructure, right? We have our business of scaling up and making cost-effective fuel cell systems to power these applications. And then it's going to be getting all the applications up to the speed that they're ready to make the shift. I mean, it took a long time before the auto industry was ready to electrify, right? I mean, electric vehicles have been around for 100 years or more, right? More than 100 years. So, I mean, getting an industry to that point and having the demand for them to make that shift in scale, and spend the investment to kind of shift over their already tried and true technologies with diesel engines that they're pretty happy with in general for a lot of things, that takes time. So you got to get them to understand the new technology, modify the vehicles, and then as that starts to scale and having all this come together at the same time, then you can make this thing where overall the total cost of ownership improves and you can provide things that the customers couldn't get with other technologies.
I asked about the green hydrogen because a lot of hydrogen naysayers say, well, the gray hydrogen isn't good enough. You know, we have to get to this full kind of, zero emission ideal.
I think it would be foolish for us to ignore the other forms of hydrogen in this nascent period where we're trying to start the thing up. The gray hydrogens can be cleaner than alternative propulsion, even though they're not, perfectly green, and they can be much lower cost, and they're much more readily available. I mean, you can put steam methane reformation out there fairly effectively in all different types of places. So I think that kind of an approach using clean natural gas, which, the natural gas, rather than venting it and burning it off, let's convert it to hydrogen.
From your house,
Yeah. So it could make a lot of sense that way. So I think there are options there that can develop. I certainly wouldn't turn my nose up on green or gray hydrogen.
Right.
It's good.
Well, good. We're going to have to wrap it up. This could go on for a lot longer time. This is really good stuff, Charlie. Thanks so much for coming on.
Thanks for having me.
Really good thing. I apologize. We didn't get to all the viewer questions, but we got inundated with them. So I think we got to a bunch of them anyway. But
Great.
thanks again, Lindsay. Great having you here.
Thanks,
and
John.
We'll keep on doing these
And
kinds of shows.
and the aforementioned Mr. Larry Burns will be here in 3 weeks, I
Oh,
believe.
that's right. Yeah, he'll be on the show.
Tell him
So,
I said hi.
yeah, we'll do that. So thanks everybody for having tuned in.
AutoLine After Hours is brought to you by Bridgestone Tires, solutions for your journey.